forms by the freezing of seawater. The total ocean area of sea ice varies annually between 5 to 8%. There is variability in sea ice extent between the two hemispheres, with southern hemisphere sea ice extent ranging from 3 to 20 million kilometres squared, and sea ice in the northern hemisphere varying from 7 to 16 million kilometres squared. Monitoring sea ice extent is of great importance as it is a sensitive indicator for global climate change. In the Earth's climate system, sea ice, and the cryosphere as a whole, plays an important role because of its interactions with the atmosphere, ocean, and land in a number of complex feedback processes. One such process is the albedo temperature feedback mechanism. Ice and snow significantly affect mass and energy exchanges as they comprise of bright, wet, and cold surfaces, reflecting a large proportion of solar radiation back out to the atmosphere and into space. This deflects a significant quantity of solar energy and is an important cooling mechanism protecting the planet from excessive global warming. If, however, the amount of energy in the atmosphere increases, snow and ice absorb more energy and melt. As a result, more ocean is exposed and the Earth's albedo is lowered. This then causes more energy to be absorbed and the cycle continues. As such, measuring sea ice extent can be used as a tool for monitoring and predicting climate change. Furthermore, sea ice plays a key role in oceanic circulation. As seawater decreases in temperature, it is able to hold more salt, and the formation of sea ice means that the remaining unfrozen water is briny, denser, and as such sinks. The seasonal formation of sea ice therefore acts to drive ocean circulation, moving energy between the equator and the poles. Monitoring changes in sea ice extent is therefore important because severe reductions in sea ice extent, coupled with freshwater melt at the poles, could not only lead to sea level rise, but could also hinder the oceanic conveyor belt. Satellite sensors monitor the large expanses of polar sea ice, primarily through the use of microwave techniques, which, unlike optical instruments, are able to provide continuous synoptic global coverage, operating in all weather conditions and during the night. Two groups of microwave instruments routinely perform sea ice detection. Firstly, passive radiometers using a range of microwave frequencies are used to observe natural surface emissions. Secondly, and the focus of this video, is scatterometers. In Earth observation, an almost daily global coverage, especially in the polar regions, is provided by a wide swath of scatterometers with general resolutions between 25 to 50 kilometers. Scatterometry is a type of active radar remote sensing, which is able to measure a number of geophysical properties of volumes and surfaces. It does this by transmitting radar pulses and receiving the backscattered energy, the intensity of which depends upon the surface roughness and its dielectric properties. Scatterometers are able to gather cross-section measurements that can help provide an insight into microwave interactions with natural surfaces and objects, as well as producing operational data that can be used to monitor different aspects of the environment. The intensity of the backscattered energy, known as the backscattered coefficient, varies according to roughness properties. For ice and snow, the geometry and roughness properties that influence backscatter include moisture content, surface roughness, and the alignment of surface scatterers preferentially. For example, as the surface roughness increases, a greater quantity of the microwave pulse is returned to the microwave source. The intensity of the backscattered energy also varies according to the dielectric properties of the target. The dielectric constant is an electrical property that influences the interaction between matter and electromagnetic energy, and is a function of wavelength and temperature. The dielectric constant is affected by the physical characteristics of the scattering medium, for example, the phase state of water, sea ice, brine concentration, and snow grain size. Measuring the relative backscatter between two polarizations allows for the separation of open water from sea ice. Furthermore, fan beam and pencil beam scatterometers are used to measure the backscatter gradients of surfaces across a range of incident angles and the azimuth angle, which allows for the detection of features which have preferred orientations. Over the last 2 decades, Scatterometry has significantly contributed to understanding the role of sea ice in global climate change. A variety of scatterometers have been used, beginning with the European Remote Sensing (ERS) satellite series in 1991, followed by NASA's NSCAT scatterometer on the Advanced Earth Observing Satellite, SeaWinds on NASA's QuickScat satellite, and then more recently the European Advanced Scatterometer ASCAT on the METOP satellite. Developments in swath width ability mean that a single instrument can now provide coverage of around 90% of the global oceans daily. Such remote sensing has revealed considerable regional, interannual and seasonal variability of the sea ice cover in both hemispheres. While satellite scatterometry does provide a wealth of valuable data enabling the mapping and improved understanding of global sea ice, it does also have a number of limitations. Firstly, due to the mix of influences that affect microwave energy's backscatter response from the surface, the interpretation of the data gathered is very complicated. For example, the QuickScat satellite can produce reliable maps for higher concentrations of the Arctic sea ice pack. However, it is less accurate at depicting lighter ice concentrations, which are generally found in marginal ice zones. Developments in scatterometers that operate at multiple frequencies may help in discriminating between the various components that contribute to the backscatter coefficient. Also, it is important to recognize that no single Earth observation instrument is able to give a full picture of sea ice. Active and passive sensors using wavelengths from the visible to microwave provide different pieces of information about sea ice and how this fits into the larger Earth climate system. The increasing assimilation of numerous data sets is the future of remote sensing science. In conclusion, satellite scatterometry plays a key role in improving the understanding of sea ice. Mapping sea ice and its spatial and temporal changes allows for a greater understanding of the role of sea ice in the Earth's climate and ocean systems.